Hello everyone, myself C Koteswaramma, working as Assistant Professor in EC Department at Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I would like to explain about the introduction of electrostatics and Coulomb's law. Before going to this electrostatics, we will see what is electrostatics. Electrostatics is nothing but study of charges which are at rest. If you take the word electrostatics, it is a combination of electro and statics. Electro here represents the charge and statics represents the stable. Here, electrostatics deals with the study of charges which are at rest or which are stable. And we can take it as a branch of physics that studies electric charges at rest. And generally, this charge may be either positive charge or negative charge, and the fields produced by those stable charges we can call as electrostatic fields. And we have different names for electrostatic fields. Electrostatic fields are also called as static electric fields or steady electric fields. And these fields are not variable with time, they are stable ones. And to explain about any theory, we need some mathematical formulations and graphical representations. Usually, for the better understanding of any innovation or any theory, we need mathematical representations and graphical representations. And here we have different mathematical representations. Those are, we can use different laws to represent any theory, and we can use theorems and equations. So here, to explain about electrostatics, we have important laws. Those are Coulombs and Gauss laws. Similarly, we have two theorems to explain about electrostatics. Those are Stokes theorem and divergence theorem. Stokes theorem and divergence theorem here help us to derive the important relations. And next, equations usually we go through for electrostatics are Poisson's and Laplace's equations. Here for electrostatic field or for static electric field, the important parameter or the important source is charge. That charge is represented with the symbol Q. And next, this charge is represented with Q, and that if it is located along a point, we can take that one as Q, and that charge may be distributed to length, surface and volume also. Okay, this is about the introduction of electrostatics and the laws, theorems, equations required for electrostatics. Electrostatics is all about the study of charges which are at rest, and to explain it clearly, the different laws we have are Coulomb's and Gauss laws. Theorems are Stokes theorem and divergence theorem. Equations, Poisson's and Laplace's equations. Here we have a question, why to study this electrostatics? We have numerous applications for electrostatics. So now we will go through those applications. So this is a core subject for electronic students, and always electronic students deals with CROs and all those. Here, if you go through the applications of electrostatic fields, the first application we can take is this one, electrostatic field concept we can use in cathode ray oscilloscope, that is in CRO, to obtain electron beam deflection. That electron beam deflection will give us the shape of any signal, and CRO is the display unit there. The basic field behind this waveform appearance is electrostatic field only. And next, the next application we can take is in inkjet printers. To obtain speed of printing and quality of the printing, we can use electrostatic fields. And even in agriculture purposes, to sort out minerals in ore separators or to sort out seeds in agriculture, and for spraying plants and trees also, we can use electrostatic fields. And next one, in electrostatic generators, we use electrostatic fields, and to produce potential. If you go through the electrostatics, we come across two important characteristic parameters. Those are electric field strength and electric flux density. That generally that electric field strength is represented with the capital letter E, and electric flux density with the letter capital D. And as we calculate electric field strength, finally we try to calculate the potential, and that to calculate that potential also, we use electrostatic fields. That we can take as one application. To produce potential, we can use electrostatic fields. And next is to produce force on charges, or to calculate force, we need electrostatic fields. And next one is in electric power transmission also we use electrostatic fields. And next is in lightning protection, to measure moisture content. Again, this is agriculture application of electrostatic field to spin cotton. And in field effect transistors, in FETs also we use electrostatic fields, or that we can take as application of electrostatic field. And in capacitors, LCDs, touchpads, capacitance keyboards, in all these we use electrostatic fields. And the other applications here are in fast baking of bread. This is general purpose application. And next, if you go through medical applications, in ECGs and EEGs, we use electrostatic field. Next is spray painting, that is also general purpose application. Next is electrodeposition, electrochemical machining, X-ray machines, computer peripherals. All these we can take as the applications of electrostatic fields. So up to now, we came to know about what is electrostatics and what is electrostatic field and why to study that electrostatic field. So as it has many applications, we try to study about the electrostatic fields. And next here, in electrostatic field, the basic source or the basic element is charge. So for the better understanding of electrostatic field, we must know about the charge, or we must have a basic idea how the charge will be and what are different charges, what are the properties of charges and what the functions of charges. So now here, so I would like to tell you about some properties and functions of the charges and how the charges will be distributed. So if you go through the charge is usually conserved one. Charge is conserved. So that means it cannot be created or cannot be destroyed. It can neither be created nor be destroyed. Charge is conserved one. And usually when a charge is accelerated, that produces some current. And that current finally results in magnetic field. And that field, the produced field, we can call as electromagnetic field. Then the electromagnetic field is moving with the speed of light. And generally charges are surrounded by electric and magnetic fields. Always moving charges create some current that can produce magnetic field. And generally charge may be either positive charge or negative charge. Those we can take as types of the charges. And under the properties, we can take charge as a conserved one. If it is moving, it is creating electromagnetic field which is moving with the velocity of light. And if you go through the distribution or orientation of the charge may be located at a point, or it may be distributed for a line, it may be distributed to a surface, and it may be distributed to a volume. Depends upon how it is distributing. We can call the charge as point charge, line charge, surface charge, or volume charge. First, we will go through point charge. Point charge is confined to a point. See, from the name itself, point charges are confined to a point. That means if you take the volume of point charge, its volume will be 0. Usually that point charge is represented with the letter capital Q, and units for point charges are Coulombs. The second possible configuration of the charge is line charge. By joining few points, generally we can form a line. If the charge is distributed along a line, we can call that charge as line charge, and that line charge is represented with the letter rho suffix L. In the suffix we have the letter L. That suffix letter represents along what that is distributed. Here rho is generally represented for charge density term. Here rho L means charge density along a line. To get charge density, we must take charge per. Here for line charge density, we must take charge per unit length. And its units are rho L. We can take rho L. Rho L equal to charge density we can represent with rho. Charge density we can represent with rho suffix L, and this is equal to charge per unit length. So as the units of charges are coulombs and units of length is meter, so units per charge line charge density is coulomb per meter. And the next one is surface charge density. Surface charge density is represented with next one is surface charge density. So as the charge density is represented with rho and now it is distributed or it is confined to the surface, we can take the representation of surface charge density as rho S. And this rho S equal to, this is surface charge density. This is the charge per unit area. Unit surface area we can take. And here the representation of charges and area is, yes, surface area. Area here means surface area. No, so now rho S equal to Q per S. And its units are as units of Q, charge is coulomb, and units of surface area is meter square. Units of surface charge density is coulomb per meter square. So this is about surface charge. And the next charge distribution is along a volume. Volume can cover all the directions. So volume itself includes line and charge, line and surface. So here volume charge density is represented with the symbol rho suffix V, which is charge per unit area or unit volume. So unit volume units are meter cube and charge units are coulombs. So finally units per volume charge density is coulomb per meter cube. So if you take line charge, it may has length, it has only length but no width or breadth. Similarly, if you go for surface charge density, it has both length and width but no breadth. But whereas in case of volume charge density, it has length, breadth and width. 3 directions it has. So this is about how the charge is distributed at a point, along a line, along a surface and along a volume. Now this charge is generally expressing a force in the presence of a field. So as we find presence of charge, usually there is a field. So to explain about that field, now we have 2 laws. First one is Coulomb's law and second one is Gauss law. Now first we will go through Coulomb's law. Coulomb's law is formulated by the scientist named Coulomb. It deals with the forces on point charges, and usually these charges may be either positive or negative. If both the charges are positive, then they can repel. Or if both the charges are like charges, then they can repel, and unlike charges will attract. So now, if you go through the statement of Coulomb's law states that here we are trying to calculate the force with the help of Coulomb's law, and Coulomb's law states that the force of attraction between 2 point charges. Here we are assuming that there are 2 point charges and they can represent with the symbols Q1 and Q2. Q1 and Q2. Q1 and Q2 are representations of charges here. And now if we have 2 point charges, then they experience some force on each other. Q1 can experience some force on Q2. Similarly, Q2 can experience some force on Q1. Now we use Coulomb's law to calculate what amount of force Q1 exerts on Q2. Similarly, what amount of force Q2 exerts on Q1. So now, if you go through the statement of Coulomb's law, in case of 2 point charges, the force of attraction between 2 point charges Q1 and Q2, that is represented with the letter F, and that is generally proportional to the, that is usually the force of attraction between these two charges is generally along the line joining them, and that is directly proportional to the product of both the charges. Here both the charges are Q1 and Q2. Force is directly proportional to the product of charges Q1 into Q2, and that is inversely varying with the square of the distance between them. Here the distance between both the charges is R, and now force is inversely proportional to the square of the distance between them. So now here if we take two charges, here this is origin point. Now both the charges Q1 and Q2, this is Q1 charge and this is Q2 charge. Here both the charges Q1 and Q2, they are located at a distance of R1 and R2 units. Here Q1 is at a distance of R1 from the origin and Q2 is at a distance of R2 from the origin. Now the distance between these two charges Q1 and Q2, this distance we can take as R. So now if the distance between both the point charges is R units, then the force is inversely varies with R square. So now the statement for Coulomb's law here is F is directly proportional to Q1 Q2 by R square. It means force is varying proportional to the product of charges, and it is inversely varying with the square of the distance between them. So now here we can replace this proportionality constant with the letter K, and it has some value. K is a proportionality constant. Its value is 1 by 4 pi epsilon naught. And here where epsilon naught is permittivity of free space and its value is 8.854 into 10 to the power of minus 12, and units for it is farads per meter. So now as we know the value of epsilon naught, if we go through the value of K, K is 1 by 4 pi, and by substituting epsilon naught value, K value is 9 into 10 to the power of 9 meter for farads. This is about the K. So now this one we can take as, this equation 1 we can take as the force in scalar form. We can take this one as force in scalar form. Now here as the fields are dealing with vector parameters, we try to represent this force in vector form. That we will see now. So now to calculate the force in vector form means you must mention the direction. So in vector form we can calculate force on Q2 due to Q1. That means as we are moving from Q1 to Q2, we can calculate force on Q2 due to Q1. That we can represent as F12. Here F12 is the force on second charge Q2 due to Q1. As we all know that as we place 2 point charges Q1 and Q2, both the charges are experiencing some force on the other charge. Now we are trying to calculate the force on both the charges, and now here the direction is important one because we are taking the force in vector form. Here F12 represents, now we have two charges Q1 and Q2, Q1, Q2. Now Q1 is experiencing some force on Q2. That means that we are moving from Q1 to Q2. Now Q1 is the source and Q2 is the destination. Now we are trying to calculate the force on destination point due to a point charge Q1, which we can consider as a source. Now here in this F12, the subscript 12, in this 12, the 2 represents on which charged particle we are calculating force and due to which one. F12 means force on Q2 due to Q1. So while calculating F12, we are moving in the direction from Q1 to Q2. Towards Q2 we are moving. That F12 here is the force, in case of Coulomb's law, the force equation is F12 equal to Q1, Q2. Here both the charges are Q1 and Q2. Their product is Q1 into Q2. F12 equal to Q1, Q2 by 4 pi epsilon naught R square. Square of the distance is R square into unit vector. Unit vector now is AR12. AR12 is unit vector along R12 direction. This is R12. Here we have R12. R12 represents the position vector as we are moving from 1 to 2. So now here AR12 value is, AR12 is unit vector, AR12 is R12 displacement vector. AR12 here represents unit vector which is equal to position vector along R12, position vector along R12 divided by magnitude of the position vector along R12, magnitude. Okay, to calculate position vector, this we have to consider. Position vector is R2 minus R1 and its magnitude. Magnitude here we replaced with one more symbol which is R. This is that one. R equal to R12, magnitude vector. Now here by substituting this position vector and magnitude vector, AR12 value is R12 by R. Now we have to substitute this C in equation 4. This is equation 4. F12, equation 4 is F12 equal to force on Q2 due to Q1, which is equal to Q1 Q2 by 4 pi epsilon naught R square into AR12. Now by substituting this AR12 in equation 4, the final equation we have is F12 equal to Q1 Q2 by 4 pi epsilon naught R12 by R cube. Q1 Q2 by 4 pi epsilon naught R12 by, you have R square in the denominator already, and one more R has come by writing the meaning of unit vector. So final equation here is F12 equal to Q1 Q2 by 4 pi epsilon naught R cube into R12, where R12 is position vector. This, by writing this position vector, in the numerator we have R12 which is position vector. Meaning of position vector is R2 minus R1. Sorry, R12 is displacement vector. Displacement vector R12 is position vector R2 minus position vector R1 divided by magnitude vector. Magnitude R equal to modulus of position vector's difference. R2 minus R1, displacement vector R, position vector's difference to the power of 3 whole cube. So now this is about the force on Q2 due to Q1. And if you move from Q2 towards Q1, there we can take Q2 as the source and Q1 is the destination. Then we can represent the force on Q1 due to Q2 as F21. And that F21 may be similar to R. F21 is similar to F12 in magnitude, but the direction changes. As the direction changes, negative sign will come into picture. This F21 equal to minus F12. So here F21 is the force on Q1 due to Q2. In the suffix, second number represents the destination source, the destination charge, and the first number represents the source charge. F21 represents the force on charge 1 due to charge 2. Here charge 2 is the source charge. And the field charge, or destination charge or the field charge here is Q1. So now in this way we can calculate force on Q1 due to Q2. Similarly, force on Q2 due to Q1 in vector forms. So, see, this is about the case if we have 2-point charges. If there are multiple charges, if there are n number of charges, then we can calculate force on two charges separately and we can add them. So that we can take as superposition principle. Superposition principle is the response of the system by applying multiple inputs is equal to response of the individual, sum of the response of the individual inputs. Here, if you take n point charges and if their locations are Here take n point charges and name them as Q1, Q2 up to so on Qn. And they are located at the distances of R1, R2 up to so on Rn with respect to origin. Now here if you take origin point and if you have a point charge Q here, and if you take one other charges Q1, Q2 up to so on n charges, and all their positions are position vector here is R. Similarly, distance, this is origin. Distance between this Q1 and origin here is R1. Similarly, distance between this one, origin and Q2 is R2. And distance from this to origin to Qn is Rn. If these are the distances, these distances we can take as position vectors. Now here what I am trying to do is, I am trying to calculate force on the charge Q due to all other charges. So now here with the help of Coulomb's law in vector form, I can calculate force on Q due to Q1, force on Q due to Q1, F on Q due to Q1, that we can force on Q due to Q1. Force on first charge due to Q1 that I am taking is F1. Similarly, force on Q due to second charge Q2 as F2. Up to so on force on Q due to nth charge, which is, so this is Q, and nth charge is Fn. So to calculate the total force F, now here I am applying superposition principle. So to get total charge by using superposition principle, we have to add all the forces. Total force is F. This is the total force on Q due to multiple charges. And these are F1, F2, F3 are individual charge force. Force due to Q1, Q2 up to so on Qn on Q. So now by taking the help of Coulomb's law in vector form and writing their meanings, F1 here is, this gives us F1 term, F2, Fn. F1 is force on Q due to Q2. From the definition or from the statement of Coulomb's law, force on Q due to Q1 is equal to the product of charges Q and Q1. Here both the charges are Q and Q1. Q1 by 4 pi epsilon naught into displacement vector. Displacement vector between charge Q and Q1. Here the destination point or the field point is Q and its position vector is R. So R minus R1. Source is located at a position vector R1, R at a distance of R1 units. So you have to take R minus R1 divided by R minus R1 whole cube plus F2 is the force on Q due to Q2. So to obtain it, we must take the product of Q, Q2 into displacement vector is R minus R2, because here the field point is Q, which is at a distance of R units from the origin, and the source point is Q2. It is at a distance of R2 units. So R minus R2 divided by 4 pi epsilon naught, its magnitude whole cube. Magnitude is modulus of R minus R2 whole cube. Similarly, for nth charge, the effect of nth charge on Q. So now by taking the generalized equation here, F equal to, by taking this Q by 4 pi epsilon naught is common term here. By taking it out, F equal to Q by 4 pi epsilon naught, and by writing it in summation form, here the charges are from 1 to n. So here sigma k equal to 1 to n Q into R minus RQK. Sorry, this one is QK, sorry. This is QK. QK into R minus RK by modulus of R minus RK whole cube. This is about the force on a point charge Q if there are multiple point charges. This is also in vector form. So now, as we go through Coulomb's law, we can easily calculate the force on point charges. And why to calculate this force is, if you go through electrostatics or electric field, two important characteristic parameters of electric fields. Two important characteristic parameters are electric field strength E and electric flux density D. Our final aim is we need to calculate these two important parameters. So now we are taking the help of Coulomb's law to calculate these two important parameters. In that, first we will go through electric field intensity, which is represented with capital E. That electric field strength or electric field intensity, these two are synonyms for this E. Electric field intensity is also called as electric field strength. This we can calculate as we know the value of force is E equal to F by Q. If it is a case of point charge, then you can take E as limit Q tends to 0 F by Q. Here Q tends to 0 represents the charge is confined to a point. So if it is a point charge case, E you can take is F by Q. This F we can take from Coulomb's law. So as we know force and point charge, we can easily calculate the important parameter, which is electric field intensity. This is the case of one point charge. So now, if you take electric field intensity in vector form, this is equal to F by Q is in vector form, in scalar form. If you want to take this E in vector form, there we can take Q as, F equal to, we know the meaning of this F. From Coulomb's law, we can take F as Q1 Q2 by 4 pi epsilon naught R square into AR. Here, we will take both Q1 and Q2 as Q itself, then E equal to Q into Q. QQ by 4 pi epsilon naught R square into AR. This is the meaning of F divided by, now you have a Q here. So this Q and 1Q gets cancelled. And this field intensity value is Q by 4 pi epsilon naught R square into AR. Again, by writing the meaning of this AR, unit vector AR, here we have Q common, 4 pi epsilon naught, and this AR is displacement vector, which is R minus R dash divided by R minus R dash Q. This is about point charge which is located at a distance of R dash units. If you have 2 point charges and if one is at R and one more is at R dash, this is the equation for field intensity. If there are n point charges, Q1, Q2 up to so on Qn, then we have to calculate electric field intensity again by using superposition principle, similar to force calculation case. There what we have done is, we calculated force on individual charges, on a point charge due to all other charges, and finally we added them to get the total force. Similarly, here also to get the total electric field intensity, we have to calculate the field, individual field. That we can take as, if it is first charge case E1, E2, up to so on En, and by calculating all the field intensities individually and to get total field, we can add them. And equation for E is, if you take E1, if you take the case of E1, this is E1. If you take the case of E1, here E1 is nothing but the field intensity due to a point charge Q1, and that Q1 is located at a distance of R1 units from the origin. So, equation for this E1, this is E1. E1 is Q1 divided by 4 pi epsilon naught 4 pi epsilon naught, and displacement vector here is r minus r1, because here we are trying to calculate force on q due to q1, and q1 is at a distance of r1 unit, so r minus r1. Then displacement vector is r minus r1 and its magnitude r minus r1 whole cube. Similarly, to calculate E2, we must take Q2. This Q1 can be replaced with Q2 and R1 can be replaced with R2. So in that way, by calculating E1, E2 up to so on En, and by adding them, we can get total electric field strength value. And this is the generalized equation. Now here 1 by 4 pi epsilon naught is common, and then by taking the summation of all the charges here, K takes the values from 1 to N, and then this is general representation for charge Qk into R minus Rk. We have to remember this one. This is not Rk minus R, this is R minus Rk. Always destination point minus source point we have to consider. Divided by R minus Rk whole cube. So final equation is 1 by 4 pi epsilon naught sigma k equal to 1 to N Qk into R minus Rk by modulus of R minus Rk whole cube. This is the electric field intensity if there are n point charges. So now this is the case of R. This is the equation for electric field intensity if it is a point charge case. And as we all know that charge is not confined to a point, it may be distributed along a line, along a surface or along a volume. If the charge is distributed along a line, along a surface, along a volume, in all the cases we have to derive the equation for electric field intensity. So now here this is about the representation of different charges. The first one is representation for point charge. Here we are taking the case of positive charge. This may be plus q or minus q. Here I am taking the case of plus q. And now the first case is point charge. Here charge is confined to a point. And the second one is line charge. In this case, charge is distributed along a line. And in surface case, charge is distributed along a surface which has both length and width. You don't have any breadth. And for the fourth case, charge is distributed along a volume. Here volume has all three dimensions: length, width and breadth. And those charges we can represent with the symbols rho L. If it is line charge case, that is rho suffix L. Charge density along a line and units are coulombs per meter. Similarly, if it is a surface charge per unit surface area or unit area, units are coulombs per meter square. Similarly, for rho V means volume charge or volume charge density, that is obtained by taking charge per unit volume. So units here are coulomb per meter cube. So now as we derived the field strength equation in case of point charge, and by getting the relation between this rho L, rho S, rho V and Q, we can get the equation for E in terms of rho L, rho S and rho V also. For that one, here what I am trying to do is, I am trying to give the representation of rho L in terms of Q, similarly rho S in terms of Q and rho V in terms of Q. So here rho L is nothing but line charge, which is charge per unit length. Here I am taking unit length dl, and so now as I am taking dl here, I will take dq. Differential charge and differential length are a small charge and small length. Rho L here is, generally rho L is Q by L. Here I am taking only differential charge and differential lengths. Differential length connected to, if the total charge is Q, if the total charge connected to total length is L, as here I am taking differential length or smaller length, the charge confined to this dl is dq. So rho L equal to dq by dl. And now from this dq is rho L dl. And our final aim is, we need total charge Q, because this field intensity equation is in terms of total charge Q. So if you take equation 8 E equal to Q by 4 pi epsilon naught R square into AR. So as we know Q, we can substitute that one to get the value of E. So now here I am trying to calculate Q as we need Q in the equation. So Q, we will get Q by integrating this rho L along dl length. So Q equal to rho L d, this one. Similarly, we can write rho S as dq by ds, and by cross multiplying Q equal to rho S ds, integral rho S ds. Similarly, for volume charge case, for volume ds is nothing but here, I'll write rho S meaning here. Rho S is nothing but surface charge density. Rho S is nothing but surface charge density, which is charge per unit area. Here I am taking differential charge and differential area. So now from this rho L we can write, as we need Q, we can write Q as rho S ds. Sorry, dq is rho S ds, and to get Q we have to integrate this one. This is this equation. And next, in case of volume charge also, rho v equal to dq by dv. And again by cross multiplying and integrating we will get Q value. Now we can directly substitute this rho L, rho S and rho V in the first equation, 8th equation. Now here, by substituting the meaning of Q in terms of rho L, this is the equation. There we have equation is Q by 4 pi epsilon naught R square into AR. Now this Q meaning is, sorry, Q from that is Q equal to integral rho L dl. So now by replacing Q here, E equal to integral rho L dl by 4 pi epsilon naught R square into AR. Similarly, in case of surface charge, so now here Q is replaced with surface charge. Q is integral rho S ds by Q by 4 pi epsilon naught R square into AR. Now Q is integral rho S ds. So final equation for E, if it is the case of surface charge, is integral rho S ds by 4 pi epsilon naught R square into AR. Similarly, if it is volume charge case, we can replace Q with integral rho v dv. Now E, field intensity or field strength in volume charge case is integral rho v dv by 4 pi epsilon naught R square into AR. This is about the field intensity equations in case of line charge, surface charge and volume charges. So finally, by clearly understanding the Coulomb's law, we can calculate force and then field intensity parameters, or field strength or field intensity E. So F, force, and E in case of point charge, line charge, surface charge and volume charge, we can derive with the help of Coulomb's law. So all those we can consider as applications of Coulomb's law. If you go through the applications of Coulomb's law, the first application we can get from Coulomb's law is we can easily calculate the force between point charges. And then as we calculate force, we can calculate electric field intensity or electric field strength. And then as we know electric field strength and force, later we can calculate the potential also, V also. And then if you go through the limitations of Coulomb's law is applicable for point charges which are at rest. That we can take as one of the limitation of Coulomb's law. And next one is, we cannot apply Coulomb's law when the charges are of arbitrary shape. These are limitations we can take. And one more limitation we can take for Coulomb's law is, distance R cannot be determined accurately as the centers of arbitrarily shaped charged bodies cannot be identified accurately. If the center of the charged body, if we cannot determine the center of charged body, we cannot calculate the distance between charge and the origin point. These are the limitations of Coulomb's law. So this is all about the introduction of electrostatics and Coulomb's law. What are the points that we gone through this introduction in this topic is, So if you go through the electrostatics is about the study of charges which are at rest, and those charges may be either positive charges or negative charges. If there is a charge, it experiences some force that creates some field, and to calculate that force parameter, we go through this Coulomb's law. And if you go through the statement of Coulomb's law, uh, Coulomb's law statement is, we try to calculate force with the help of Coulomb's law. That force is along the line joining between the charges generally, and that is directly proportional to the product of both the charges and inversely varies with the square of the distance. So after calculating force, we can calculate field intensity parameter, that is E in case of point charge, line charge, surface charge and volume charge. And Coulomb's law, by using Coulomb's law, we can calculate force in case of point charges only. So this is all about the introduction of electrostatics, Coulomb's law, application of Coulomb's law and limitations of Coulomb's law. Okay. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.